In this lesson, we're going to do an introduction to rates of change. And a few important points to start here, just some terminology. In math and science, when we talk about distance, note that we're referring to the total distance traveled by an object. And that total distance is never given using a negative value. It's always a positive value that is used to describe distance. Now, displacement, on the other hand, refers to an object's position relative to some fixed point. Notice that displacement may be a negative value. So what usually happens is we set some direction as being the positive direction, and then the opposite direction is the negative direction. Similarly, when we're talking about how distance and displacement are changing, we have a couple of words that we use. The first of which is speed. Now, speed refers to how fast an object is traveling without regard to direction. So since we're not referring to direction when we talk about speed, speed is never given a negative value. Velocity, on the other hand, refers to how fast an object is traveling and the direction of its motion. Now, since we're including the direction of motion here, velocity can be given or described using a negative value. And once again, usually what happens is we have some direction is the positive direction, and then the opposite direction to that is the negative direction. So let's do a little example here. Your good friend Juanita, and perhaps you didn't know you had a good friend Juanita, but you do, and she went for a walk yesterday. She started at her house, walked for a bit, stopped for lunch, walked to the movie theater, watched a movie, and then went home. And we have a displacement time graph here that describes her journey. So let's ask ourselves some questions about this journey. First of all, when did Juanita stop for lunch? Now, remember, we're measuring displacement on the vertical axis here, and we're measuring time on the horizontal axis. So how can we tell when Juanita stopped for lunch? Well, if she was stopped, her displacement would not be changing. That is, you can think of it as her distance from home would not be changing, which means for a period of time, we should be at the same displacement. Now, we see that happens in two places. First of all, here, where we're at a displacement of 4 kilometers. And how long is that interval there? Well, notice that 4 squares is 1 hour, so each of these little squares here is 15 minutes. So this interval here must be 30 minutes or a half an hour. But we also have the same thing happening up here, where we have a 45-minute time interval where the displacement is 5.5 kilometers and it doesn't change. Now remember, she stopped twice, once for lunch and once to watch a movie. So this one must be where she stopped for lunch, and this must be where she stopped to watch the movie. So right here, we could say that 1 hour after leaving home is when she stopped for lunch. And once again, that's because the displacement is constant there. It's staying at 4 for half an hour. Next up, when did Juanita walk the fastest? Now, how are we going to figure this out? Well, once again, we're measuring displacement on the vertical axis and time on the horizontal axis. And let's take a look at the first parts of the journey where Juanita is moving, starting with this one here. Notice that in this part of our graph here, in 15 minutes, we have Juanita moving 1 kilometer. Okay, we can use that to come up with a speed. It would be actually 4 kilometers per hour, and we'll talk a little bit more about how we find that speed later on. But for now, notice in 15 minutes, she's moving 1 kilometer. Now, if we go to this part of the graph and look at how far she moves in 15 minutes, so that's 1 square horizontally, it is not 1 kilometer. In fact, it's not even half a kilometer. So down here, 15 minutes, 1 kilometer movement. Up here, 15 minutes, less than a kilometer, less than half a kilometer. So she must be moving faster here. Now, does that mean that the steeper segments on the graph always imply faster movement? Well, the answer is yes. Okay, for that reason, in a fixed amount of time, more displacement is being covered. Now, the next question is this the steepest part of the graph? And the answer is no. We can see over here, now this would be when she's heading home because her displacement from home is now decreasing, which means she's getting closer to her home. But notice that in 15 minutes, she travels more than 1 kilometer. So right up there in that area there would be the fastest part of her journey. And that's when she's on her way home. Okay? Just at the beginning though, because that doesn't stay the same. Notice we have a curved segment here, and we'll talk about what that means a little bit later on. How long was the movie? Well, we've already talked about that. Notice we, from the 2-hour 45-minute point to the 3.5-hour point, that's where she was stopped for the movie, and that is a total of 45 minutes. Next question, when was Juanita's maximum distance? Sorry, what was Juanita's maximum distance from home? Well, her maximum distance from home would be shown as the greatest displacement on our graph, and we see that that is right up here, and that's a displacement of 5.5 kilometers. So that is her maximum distance from home, 5.5 kilometers. Okay, moving on. At what speed did Juanita walk to the movie after lunch? Well, we know that she walked here, stopped for lunch, and then after lunch, she walked to the movie. Now, we want to find the speed at which she walked to the movie. Now, how do we measure speed? Well, we're measuring displacement in kilometers here, and we're measuring time in hours here. So if we look at this part of the graph, we want to find out how many kilometers per hour she is traveling. Now, how can we do that? Well, we're essentially going to find the slope of this line segment here, and we'll use the points at the beginning and end of the segment. Now notice that we have a 1.25 hour interval here, right? It's 5 squares, and each square is 15 minutes. So you could say that's an hour and 15 minutes, but we want this expressed in hours, so 1.25 hours. Now, how much displacement do we have in that 1.25 hours? 1.5 kilometers. Okay, notice here 2 squares is 1 kilometer, so 3 squares here is 1.5 kilometers. So she traveled 1.5 kilometers in 1.25 hours. Now, if we want to find the number of kilometers per hour, we need to divide. 1.5 kilometers divided by 1.25 hours gives us the number of kilometers per hour, which is 1.2 kilometers per hour. So that's pretty slow. So does that mean if we want to find speed using a displacement time graph, or velocity using a displacement time graph, we can just find the slope of a segment? And the answer is yes, provided that in this case, we have a straight line segment. And we'll talk later on about what happens when we don't have a straight line. Finally, some questions for discussion. What other information does this graph tell us? Well, I'll draw your attention to this part of the graph right here. Notice that it starts off quite steep, but then it gets less and less steep as we get closer to the 5-hour point. Now, what does that mean? Well, before we said the steeper that the graph is on a displacement time graph, the faster the motion is. And that is what's happening here. We have fast motion because it's quite steep, but then as it gets less steep, that must mean that the speed is decreasing. In other words, Juanita is slowing down. Now, you might ask, why did Juanita slow down so much here before she got home? Notice she didn't make it back home. I'll let you think about why that might be. One other thing that I'll mention before we wrap things up here is to think about how realistic is this graph at describing somebody's journey if they're walking. Now, what do I mean by that? Well, notice she was traveling at 4 kilometers per hour at this point, and then instantly she was stopped. Now, is that possible to go from a speed of 4 kilometers per hour to 0 kilometers per hour in an instant? And I think you'll realize that no, that's actually not possible. She'd actually have to slow down, even if she slows down very quickly. So what I'm getting at is that this sharp corner here is not very realistic. What we'd really probably see in real life is a kind of a curve that flattens out from this slope here to a slope of 0 gradually. It might be quite quickly, but it won't be so abrupt as is implied by this sharp corner. So just something else to think about there. And that is our introduction to rates of change.